Hello everyone, I am Kyoung-Hee Kim, a professor of architecture at UNC Charlotte. In this lecture, we will explore circularity in buildings, focusing on reduce. This principle of reduce is the first and perhaps most critical step toward a sustainable circular built environment. Before diving into building strategies, let's briefly define the circular economy. A circular economy is an economic system inspired by nature's cycles where there is no concept of waste. In a building's life cycle, from design and construction to operation and demolition, there are many opportunities to close loops and eliminate waste. Instead of the linear model of take, make, dispose, a circular economy does not generate waste by reusing and recycling materials for as long as possible. The goal is to minimize material input and maximize resource efficiency without extracting raw materials, while reusing and recycling materials and generating little to no waste. This slide has been discussed in other circular economy videos. The horizontal axis represents the progression of construction elements from the recycling of individual building materials to the reuse of systems and modules, and ultimately to the adaptive reuse of entire buildings. The vertical axis represents the levels of circularity. As circularity increases, both environmental and economic value increases. The adaptive reuse offers the highest benefits by preserving the entire building. In a circular economy, building materials such as crushed concrete and gypsum boards could be recycled to create new construction materials. Building elements such as used bricks and used windows can be reused to produce recycled or reused materials for renovation and new construction. Building systems such as used facade systems and structural frames could be reused for new facade claddings and structures elsewhere. Building modules such as whole rooms or units can be disassembled and reassembled to form new building modules for adaptive reuse or new construction. Adaptive reuse means nearly all the material and effort that went into the building is preserved when it serves a new purpose. Moving beyond the mindset that buildings have a fixed end of life, we should design buildings with circular use in mind. Let's look at the framework of applying circular economy principles to buildings. Within the net zero waste or circular framework, there are several key strategies. Here, we list 4 of them: reduce, recycle, reuse, and regenerate. Let me briefly explain each. Reduce, the first and most important strategy. Reduce means using less material and energy from the outset. In architecture, this could involve efficient design that meets needs with fewer resources. For example, optimizing the building size, using lighter or fewer materials without sacrificing strength, or designing for energy efficiency so smaller systems are needed. Reduce is priority number 1 in the zero waste strategy. We prioritize less material input and processing and aim to reuse them as much as possible. Many of you might be familiar with concepts like cradle-to-cradle design, which ensures materials from a building can be reclaimed and used again in equal value, or materials passports that track components for future recovery. Refer to the circular economy. Reuse video for more information. Next, construction materials and elements that cannot be directly reused are recycled. However, many building systems are not designed for easy disassembly, often resulting in the materials being crushed rather than preserved. Refer to the circular economy. Recycle video for more information. Regenerate encompasses materials that replenish resources and restore ecosystems. Refer to the circular economy. Regenerate video for more information. A typical circular economy framework in architecture involves designing out waste from the beginning, keeping products and materials in use through reuse or recycling, and regenerating resources or natural systems. One of the best ways to reduce resource and energy consumption is to avoid over-engineering or using more material than necessary for the function. Let's consider wall insulation as an example. Insulation is crucial for energy efficiency as it slows heat loss. But there is a point of diminishing energy benefits. In other words, beyond an optimal thickness, you're using more material but not getting proportional benefits. This line graph shows the thermal insulation thickness on the horizontal axis and the percent energy savings on the vertical axis. A simple way to illustrate this is by looking at the thermal resistance, R value of insulation. For instance, the first few centimeters of insulation produce large energy savings, but further thickness beyond the optimal point yields only marginal improvement. Let's say you've doubled the insulation from 10 centimeters to 20 centimeters thick, which uses more material, yet energy efficiency improves from 73% to 80%, just a few percent better. Practically, it means beyond a moderate insulation level, the energy savings per added thickness are very small. Therefore, a reduced strategy in design is to use enough insulation to meet energy and comfort goals and code requirements, but not simply maximize thickness without limit. The optimum insulation thickness varies depending on climatic conditions. Another key design choice affecting both materials and energy is the amount of glazing on a building. The window-to-wall ratio is the percentage of a facade that is made up of windows or glass, as opposed to opaque walls. Many modern buildings feature extensive glass facades, but from an energy and material standpoint, more is not always better. Windows typically have much lower insulating value than walls, even with high-performance glass. They also let in unwanted solar heat, increasing cooling load. So as the window-to-wall ratio increases, buildings often become less energy efficient. They can lose more heat in winter and gain more unwanted heat in summer. This graph illustrates the relationship between WWR on the horizontal axis and total CO2 emissions on the vertical axis. Each line color represents different window glass specifications. The graph shows an optimum WWR for least emissions. Higher WWR results in higher emissions and energy costs. The optimum WWR varies depending on building types and climate conditions. A building with around 30-40% WWR often offers a good balance. It can get plenty of daylight and views, but still have enough insulated wall area to perform well in terms of heating and cooling. Thus, from a reduced perspective, we aim to use the right amount of glazing, not the maximum amount. This means thoughtfully sizing and placing windows. Architects might design well-positioned windows that provide daylight and view where needed instead of entire glass curtain walls. By doing so, it's a win-win as we preserve comfort and functionality with fewer resources, with less glass and metal used, and energy savings. In summary, controlling the WWR is a critical strategy. We design facades to have sufficient glazing for light and aesthetics, but not so much that it undermines energy efficiency or needlessly increases material use. Another strategy to reduce energy use is to design a building cleverly tailored to its climate. For instance, the line graphs on the left illustrate varying building footprint ratios indicated along the horizontal axis and their corresponding energy consumption during both summer and winter across 4 climate zones. The vertical axis shows the heat gain, positive values, and heat loss, negative values, across summer and winter. As shown on the right, in cold climates, buildings are typically compact forms with a footprint ratio of approximately 1 to 1.1 between summer 1.0 and winter 1.3. This helps minimize exterior surface area to reduce winter heat loss. In a temperate climate, the optimum footprint ratio is 1 to 1.6. The building geometry is positioned to capture winter sun for heating benefits and to promote natural ventilation in summer for cooling benefits. In a hot, dry climate, the footprint ratio is 1 to 1.3, and the building integrates courtyards for evaporative cooling. In a hot, humid climate, the footprint is 1 to 1.7, more elongated than the one located in the hot, dry climate. Windows are protected with shading devices, and the building mass is articulated to augment self-shading. This analytical method uses climate data to guide design decisions for energy efficiency and user comfort so that architects can find solutions that fit the environment. The result is often an optimal use of materials. You put materials where they matter most for comfort and structure and avoid adding superfluous systems. Bioclimatic design yields optimum material use. This means that when you design in harmony with the climate, every element of the building is working efficiently. Our final example of the reduced principle in action involves structural engineering, specifically using materials to their full potential so we don't waste materials by over-engineering. Every material and product has its structural limits. If we know those limits, we can design structures that maximize the efficiency of each component and avoid adding unnecessary material. A deeper or thicker deck can span a longer distance between supports. Typically, off-the-shelf metal decks can span on the order of a few feet up to around 10 feet or a bit more between beams, depending on the type and gauge. For instance, a 3 composite metal deck in a thicker gauge might span about 10 feet without support. If the same deck tries to span 8 feet apart, you may be adding more steel members than necessary because the span underutilizes the deck's capability. Conversely, if you try 15 feet apart, you might end up using a very thick deck or adding intermediate supports, again extra material. Either scenario means more material usage than needed. The optimal is to push materials just to their efficient limit, but not beyond. From a reduction standpoint, we need to match the efficient span of materials according to the structural layout for optimal use. This video was supported by UNC Charlotte in collaboration with the US-ASEAN Smart Cities Partnership. For further inquiries, please contact Kyoung-Hee Kim at UNC Charlotte. Let's work together towards a sustainable future through circular economy practices in the built environment.